Across 140 million miles of cosmic darkness, a red planet waits. It glows in our telescopes like a promise, like a second chance, like the answer to humanity's deepest fear, that we are fragile, temporary, bound to a single world that could fail us at any moment. Mars has become more than a destination. It has become a dream, the backup planet, the lifeboat, the new world waiting to be claimed by those brave enough to reach it. Billionaires speak of cities beneath domed skies. Engineers draft blueprints for underground habitats. Children grow up believing that Mars is not a question of if, but when. Yet tonight, as we drift through the silence of deep thought and cosmic wonder, we must ask a question that few dare to speak aloud. What if Mars is not our salvation, but our most beautiful lie? The vision is seductive. Elon Musk stands before crowds and cameras, painting pictures of 1 million people living on Mars, of vast colonies spreading across rust-coloured plains, of humanity becoming a multi-planetary species. We must make life interplanetary, he declares, or face extinction. The timeline seems almost casual, a decade, perhaps 2. The technology, he assures us, is within reach. Starship will carry hundreds at a time. Settlement will be self-sustaining. Mars will become Earth's twin, reborn through human will and engineering genius. It is a narrative so compelling, so hopeful, that it has captured the imagination of an entire generation. But beneath the surface of this dream, in the quiet offices where planetary scientists analyze data and medical researchers study long-duration spaceflight, a different picture emerges, a darker truth whispered in academic papers and conference halls. The more we learn about Mars, the more impossible colonization appears. Not difficult, not challenging, impossible. And the dangers are not the ones we see in movies, dramatic explosions or sudden disasters. They are slow, invisible, and absolutely unforgiving. They are written into the very physics of the planet itself. Tonight we will journey beyond the promotional videos and inspirational speeches. We will examine 6 fundamental realities that make Mars colonization far more dangerous than anyone publicly admits. 6 insurmountable challenges that turn the Martian dream into a potential nightmare. From radiation that silently shreds DNA, to toxic soil that poisons everything it touches, to an atmosphere so thin and hostile it might as well not exist at all. We will explore why the human body, evolved over millions of years for Earth-specific conditions, may simply be incompatible with long-term survival on Mars. And we'll confront the trillion-dollar question that hangs over every rocket launch, every test flight, every bold prediction. Are we chasing genuine progress, or are we investing our hopes and resources in an impossible fantasy? This is not a story of despair, but of clarity, of understanding what Mars truly is, not what we wish it to be. If you're settling in for the night, let these revelations wash over you like a gentle tide of knowledge. If you're here to learn, to question, to understand the universe as it truly exists, then you are in the right place. Before we begin this journey into the Red Planet's darkest secrets, take a moment, if you would, to share where you're watching from and what time it is in your part of the world. Let us build a small constellation of curiosity, a global community bound together by wonder and the courage to ask difficult questions. Now let us drift toward Mars, not as dreamers, but as scientists, not as colonists, but as truth seekers. The red horizon awaits, and it has secrets to share. Mars appears before us, a rust-coloured sphere hanging in the cosmic darkness, silent and still. From a distance, it beckons with the promise of new horizons, a second chance for humanity among the stars. But as we drift closer, as our instruments awaken and begin their cold, methodical measurements, a terrifying reality emerges. This world is not simply inhospitable, it is actively hostile, and the first weapon it wields against all living things is invisible, relentless, and utterly unforgiving: radiation. On Earth, we are shielded, protected by an invisible fortress we seldom think about, yet without which life as we know it could never have emerged. Our planet's magnetic field stretches thousands of miles into space, deflecting the solar wind, particles ejected from the sun that stream toward us at millions of miles per hour. Above that, our thick atmosphere absorbs what the magnetic field cannot stop, filtering out the most dangerous cosmic rays, the gamma radiation, the high-energy particles born in distant supernovae and galactic collisions. We live our entire lives beneath this protective blanket, never feeling the cosmic storm raging just beyond our sky. Mars has no such protection. Long ago, perhaps 4 billion years in the past, Mars may have possessed a magnetic field of its own. Scientists theorize that a molten core once churned beneath its surface, generating the same electromagnetic shield that Earth still enjoys. But Mars is smaller, its core cooled faster, and as the internal dynamo slowed and died, the magnetic field collapsed. Without that shield, the solar wind began stripping away the Martian atmosphere itself, layer by layer, century by century, until what remains today is less than 1% the density of Earth's air. What was once a world that might have cradled rivers and lakes became a barren wasteland, exposed directly to the radiation of space. The numbers are not abstract. They are a death sentence written in particle physics. Data from NASA's Curiosity rover, which has been measuring radiation on the Martian surface since 2012 using its radiation assessment detector, reveals a grim picture. Mars receives approximately 700 times more radiation than Earth. An unprotected human standing on door, the surface would absorb around 200 to 300 millisieverts of radiation per year. To understand what this means, consider that a full-body CT scan delivers roughly 10 millisieverts. On Mars, you would be receiving the equivalent of a CT scan every few days, week after week, month after month. There is no reprieve. The radiation does not pause for sleep or shelter. It penetrates habitat walls, seeps through regolith, and bombards every living cell in your body with invisible violence. This is not merely uncomfortable, it is cellular destruction on a molecular scale. Radiation damages DNA. High-energy particles smash through the delicate double helix structure, breaking bonds, scrambling genetic information, creating mutations that accumulate with every passing day. Our cells possess repair mechanisms, molecular machinery that attempts to fix this damage. But on Mars, the damage occurs faster than the body can heal. The repair systems become overwhelmed, mutations proliferate, and with each mutation comes the growing probability of cancer. Leukemia, brain tumours, lung cancer, thyroid cancer. The list is as long as the catalogue of human tissues. On Mars, cancer is not a risk, it is an inevitability. But cancer takes time. Radiation's immediate effects are even more insidious. The human brain, that 3-pound universe of thought and memory, is extraordinarily vulnerable to radiation exposure. Studies conducted on astronauts and laboratory animals reveal that cosmic radiation does not merely increase cancer risk, it destroys brain tissue directly. High-energy particles create oxidative stress, inflaming neural pathways, killing neurons, disrupting the delicate chemistry of cognition. Memory falters, reaction times slow. Anxiety and confusion creep in, not from psychological stress alone, but from physical degradation of the brain itself. A Mars colonist would not simply live under the shadow of future cancer. They would feel their mind eroding in real time, thought by thought, memory by memory. And then there are the solar flares. The sun is not a steady, predictable furnace. It is a roiling cauldron of magnetic chaos, occasionally erupting in colossal explosions that hurl billions of tons of charged particles into space. These solar particle events are unpredictable, violent, and potentially lethal. On Earth, our magnetic field deflects these storms, sometimes creating beautiful auroras as particles stream along magnetic field lines toward the poles. On Mars, there is no deflection. When a solar flare strikes, the surface is bathed in a surge of radiation so intense that it can deliver a lethal dose in a matter of hours. NASA has documented solar events that would have killed an unprotected astronaut on Mars within a single day. There is no warning system reliable enough, no shelter fast enough to guarantee survival. A colonist working outside, repairing solar panels or drilling for water, could glance up at the pale Martian sky and have no idea that invisible death is already washing over them. By the time symptoms appear, nausea, confusion, internal bleeding, it is far too late. Acute radiation syndrome would follow within hours, and without advanced medical facilities, which Mars would not possess for decades, if ever, death would be swift and agonizing. Proposed solutions exist, at least in theory. Engineers and visionaries speak of underground habitats, carved deep into Martian rock where meters of regolith can absorb incoming radiation. They imagine colonies shielded by layers of water, using the hydrogen atoms in H2O to scatter and slow high-energy particles before they reach human tissue. Some designs feature enormous transparent domes filled with water, creating aquatic barriers between Mars settlers and the cosmos. These concepts appear on glossy presentation slides, rendered in optimistic blues and greens, promising safety through ingenuity. But the reality is far harsher than the illustrations suggest. Building underground cities on Mars would require moving millions of tons of rock with equipment that does not yet exist, powered by energy sources not yet deployed, maintained by supply chains that stretch across 140 million miles of void. Every tunnel, every chamber, every meter of depth comes at an astronomical cost in time, labor, and resources. And even if such habitats could be constructed, they would not be homes. They would be tombs, lightless caverns where humans huddle beneath the weight of an alien world, never feeling sunlight, never breathing open air, confined to artificial spaces smaller than prison cells for the rest of their lives. Water shielding is equally impractical at scale. Water is heavy. Transporting it from Earth is impossible. Extracting it from Martian ice requires energy, machinery, and time. Surrounding even a modest habitat with enough water to significantly reduce radiation exposure would require thousands of tons. And water is not just a shield. It is life support. It must be recycled, purified, stored, and protected from freezing in Mars's sub-zero temperatures. Using water as a radiation barrier is a luxury that a struggling colony, fighting daily for survival, simply cannot afford. Then there is the question of children. If Mars is to be a true colony rather than a temporary outpost, humans must reproduce. But pregnancy on Mars may be biologically impossible. The developing fetus is exquisitely sensitive to radiation. During the first trimester, when organs and neural structures are forming, even moderate radiation exposure can cause severe birth defects, cognitive impairment, or spontaneous miscarriage. On Mars, where radiation levels are 700 times higher than Earth, carrying a pregnancy to term would be an act of unspeakable cruelty. No amount of shielding short of meters-thick barriers could protect a developing child. The radiation would seep through, particle by particle warping, cellular division, scrambling the genetic instructions that guide a human being from a single cell to a living infant. Even if, through extraordinary measures, a child were born on Mars, they would inherit a genetic legacy of accumulated mutations. Radiation damage is not always immediately lethal. Some mutations are passed to the next generation, encoded into sperm and egg cells, carried forward into the DNA of offspring. Over successive generations, these mutations would compound, genetic disorders would proliferate, immune systems would weaken, lifespans would shorten. A Mars colony would not evolve into a thriving civilization. It would spiral into genetic collapse, each generation weaker and more fragile than the last, until the population could no longer sustain itself. This is not speculation. This is biology. The extinction timeline for a Mars colony, unprotected from radiation, can be measured in decades, not centuries. Within 50 years, the first generation of colonists would succumb to cancer, neurological degeneration, and organ failure. Their children, if any survived birth, would face even steeper odds, their bodies already compromised before drawing their first breath. By the third generation, the colony would be a shadow of its founding population, a dwindling community of sick, dying individuals clinging to existence in underground warrens, their dreams of a new world reduced to a desperate struggle for one more day of life. The Curiosity rover, still trundling across the Martian surface, continues to measure this silent apocalypse. Its instruments do not judge, they simply record. Day after day, year after year, the data accumulates, a relentless testament to the reality that Mars is not a frontier waiting to be tamed. It is a graveyard waiting to be filled. From orbit, Mars appears serene, a quiet red sphere, patient and ancient. But beneath that stillness lies a storm of invisible fury. Cosmic rays born in the death throes of distant stars, solar particles flung from our own sun's turbulent corona, gamma radiation from galactic nuclei millions of light years away. All of it rains down upon the Martian surface without mercy, without pause, without end. To stand on Mars is to stand naked before the universe, and the universe does not care. It does not notice. It simply delivers its radiation, particle by particle, photon by photon, until nothing living remains. This is the first and most fundamental barrier to Mars colonization. Not engineering, not economics, not politics. It is the simple, immutable fact that Mars will cook you from the inside, slowly, inevitably, completely. And no amount of optimism, no glossy presentation, no billionaire's vision can shield you from the cold mathematics of particle physics. The radiation death trap is not a problem to be solved. It is a reality to be accepted, and it is only the beginning of Mars's hostility toward life. Beneath the rusty surface of Mars lies not treasure, but poison. Every grain of Martian soil contains a chemical threat so pervasive, so deeply embedded in the planet's geology, that it transforms the dream of colonization into a nightmare of contamination. Welcome to the reality of perchlorate salts, the invisible enemy that makes Mars not just inhospitable, but actively toxic to human life. Perchlorates are chemical compounds, salts containing chlorine and oxygen, that exist across the Martian surface at concentrations averaging 0%. That figure may sound small, insignificant even, but consider this. At such concentrations, Martian soil is more toxic than many industrial waste sites on Earth. These compounds attack the human thyroid gland, disrupting the production of hormones essential for metabolism, growth, and neurological function. Prolonged exposure leads to thyroid dysfunction, metabolic collapse, and developmental damage. For pregnant women, the consequences are even more severe. Perchlorates cross the placental barrier, threatening fetal brain development. The soil beneath our feet on Mars is not neutral ground. It is a chemical minefield, and every step stirs its toxins into the air. The discovery of perchlorates on Mars came through NASA's Phoenix lander in 2008, confirmed later by the Curiosity rover. Scientists initially viewed this finding with cautious optimism, noting that perchlorates could theoretically be used as rocket fuel oxidizers or even as a source of oxygen. But the darker implications soon became clear. These compounds are not isolated to a few regions. They are global, embedded in the regolith, the very dust and dirt that blankets the planet. Mars is not merely covered in toxic soil. Mars is toxic soil, down to depths we have yet to fully measure. On Earth, we encounter perchlorates primarily as industrial contaminants in groundwater, near rocket manufacturing facilities or fertilizer plants. Even at concentrations measured in parts per billion, they trigger environmental cleanup operations and public health warnings. Mars has perchlorates at concentrations measured in parts per hundred. The comparison is staggering. What we consider a hazardous waste site on Earth is pristine compared to the average handful of Martian dirt. Now imagine living on Mars. Imagine constructing a habitat, sealing airlocks, filtering air, doing everything possible to create a safe interior environment. Then imagine a dust storm. Mars is famous for its planet-wide dust storms that can last weeks or months, blotting out the sun and coating everything in a fine crimson powder. This is not merely an inconvenience. Every dust storm becomes a chemical weapon, and perchlorates are its ammunition. Martian dust is extraordinarily fine, microscopic particles smaller than a human red blood cell. It is also electrostatically charged due to constant friction in the thin, dry atmosphere. This charge causes the dust to cling to surfaces with remarkable tenacity. Fabrics, equipment, spacesuits, every surface that ventures outside becomes contaminated. When astronauts return through airlocks, no matter how carefully they brush themselves off, the dust follows them inside. It adheres to clothing. It embeds in fabric seams. It infiltrates mechanical joints. And with it come the perchlorates, riding every particle like molecular poison. The Apollo astronauts experienced this phenomenon on the Moon, and their testimony is sobering. Lunar dust, though chemically different from Martian soil, shares similar physical properties: extremely fine, abrasive, and electrostatically charged. Apollo astronauts reported that dust infiltrated everything. It hung in the air inside the lunar module despite careful dust mitigation procedures. Eugene Cernan, commander of Apollo 17, described how the dust got into everything and how they ate dust despite aggressive cleaning. Harrison Schmitt developed what Mission Control called lunar dust hay fever, an allergic reaction to dust particles he inevitably inhaled. Now add perchlorates to that scenario, and you have a recipe not for temporary irritation, but for chronic poisoning. No airlock system ever designed can create a perfect seal. Dust will enter habitats. It will contaminate water recycling systems. It will settle on food preparation surfaces. It will be inhaled by inhabitants. And because perchlorates dissolve readily in water, they will concentrate in the very recycling systems designed to keep colonists alive. The closed-loop life support systems necessary for Mars survival become, paradoxically, mechanisms for concentrating toxins. Every breath, every meal, every drop of recycled water becomes a potential exposure pathway. The agricultural nightmare extends even deeper. If humanity is to colonize Mars, we must grow food there. Shipping supplies from Earth is economically and logistically impossible for permanent settlement. Yet Martian regolith cannot support Earth crops, not without extensive energy-intensive detoxification. The perchlorates that saturate the soil are directly toxic to plants. Studies conducted with simulated Martian regolith show that most Earth crops, when planted in untreated Mars-like soil, either fail to germinate or grow stunted and contaminated with perchlorates absorbed through their roots. Detoxification is theoretically possible. Perchlorate-reducing bacteria exist on Earth, microorganisms that can break down these compounds. Researchers have experimented with introducing such bacteria to Mars regolith simulants, and the results show promise, but at a devastating cost. The process is slow, requiring weeks or months per batch of soil. It demands water, nutrients, and carefully controlled conditions. Most critically, it requires energy, enormous amounts of energy, to maintain bioreactors at appropriate temperatures and oxygen levels in Mars's frigid, near-vacuum environment. Consider the scale required. A single colonist needs approximately 50 square meters of growing area to produce sufficient food. A colony of 100 people would require 5,000 square meters of agriculture. Every square meter of that space needs topsoil, not just surface regolith, but deep, biologically active soil. On Earth, such soil develops over centuries through natural processes. On Mars, we would need to manufacture it, batch by batch, treating toxic regolith in industrial-scale bioreactors running continuously. The energy requirements alone would consume the majority of a colony's power generation capacity, leaving little for habitats, life support, or other essential systems. And here we encounter the water extraction paradox, perhaps the cruelest irony of Martian colonization. Mars has water, locked in polar ice caps and subsurface ice deposits. This ice represents the most accessible water source for any Mars colony. Yet measurements from orbit and surface analysis reveal that Martian ice contains perchlorates. Not just trace amounts, substantial concentrations. The very resource we need most for survival is contaminated with the same toxins that poison the soil. Extracting usable water from Martian ice requires melting it, then treating it to remove perchlorates. Current water treatment technologies can accomplish this, but again, only with significant energy expenditure. Reverse osmosis, ion exchange resins, catalytic reduction. Each method works, but each requires power, replacement materials, and generates waste that cannot simply be discarded in a closed habitat environment. On Earth, we purify water from contaminated sources all the time. We do it with vast infrastructure, supply chains for replacement parts, and the luxury of simply flushing contaminated waste back into the environment or into designated disposal sites. Mars offers none of these advantages. Every process must be perfect, every resource conserved, every waste product managed indefinitely. Experiments conducted in simulated Mars environments reveal the true scope of the challenge. Researchers have attempted to grow plants in perchlorate-contaminated regolith treated with various methods: washing with water, bacterial reduction, and chemical neutralization. The results are consistent. Even after extensive treatment, perchlorate levels in the soil often remain high enough to contaminate crops. The most effective treatments reduce perchlorates to safe levels, but only after consuming resources equivalent to several times the mass of the soil itself. In effect, it would be more efficient to ship clean soil from Earth than to detoxify Martian regolith on site. An absurd conclusion, but one grounded in thermodynamics and chemistry. The dust itself presents additional complications beyond chemical toxicity. Martian dust particles are not smooth and rounded like desert sand on Earth. Under microscopy, they appear angular, jagged, covered in sharp crystalline structures. These particles are formed through eons of meteorite impacts and lack the erosive weathering that softens Earth sediments. When inhaled, Martian dust acts like microscopic glass shards, embedding in lung tissue and causing persistent inflammation. This is before considering the perchlorates. Add the chemical toxicity, and you have a substance that damages the lungs mechanically and chemically simultaneously. Some proponents of Mars colonization suggest that these challenges are solvable with sufficient technology and resources. They point to advancements in materials science, robotics, and biotechnology as potential solutions. But this view fundamentally misunderstands the nature of the problem. This is not an engineering challenge with a clever solution waiting to be discovered. It is a perpetual resource drain, an endless battle against a planetary environment chemically hostile to human biochemistry. Every system designed to mitigate perchlorate contamination requires maintenance. Filters clog, bacteria die, membranes degrade. Each component eventually fails and must be replaced. In a Mars colony, replacement parts cannot be ordered overnight from Earth. They must be manufactured on site or shipped at enormous cost with years of lead time. A single point of failure in water treatment could poison an entire colony. A breach in agricultural contamination protocols could render food supplies toxic. The margin for error is not merely slim, it is non-existent. Comparison to Earth's most toxic sites reinforces this grim reality. The Chernobyl exclusion zone, Love Canal, the Berkeley pit, these are names synonymous with environmental catastrophe. Yet in each case, the contamination is localized. Remediation is theoretically possible. Natural processes gradually dilute and contain the worst toxins. Mars offers no such mercy. The contamination is global and permanent. There is no clean site to relocate to. There is no natural biosphere to gradually metabolize toxins. There's only an entire planet of poison, and we would be asking colonists to live in it, breathe it, grow food in it, and raise children in it. The poisonous planet is not a problem to be solved. It is a fundamental characteristic of Mars, written into its geology, embedded in its ice, suspended in its atmosphere. Every breath of Martian air filtered through life support systems, every plant grown in treated soil, every drop of purified water carries with it the shadow of perchlorates. The infrastructure required to survive this chemical siege would need to operate flawlessly, perpetually, with no respite and no room for failure. This is the reality hidden beneath the romantic vision of Martian colonies. Not red deserts waiting to bloom, but toxic wastelands that actively resist human habitation. The soil does not merely lack nutrients. It contains compounds that poison our bodies at the cellular level. The dream of terraforming Mars begins with the assumption that we can overcome these obstacles. But perhaps the more honest question is, should we even try? When the very ground beneath our feet is hostile to life, when every resource we need is contaminated, when survival requires an endless expenditure of energy just to keep toxins at bay, at what point does colonization become not ambition, but folly? The poisonous planet waits in silence, its rusty surface concealing chemical threats that no spacesuit can fully protect against, no habitat can perfectly exclude. And as we turn our gaze to the next challenge, we must ask ourselves, if the soil itself is our enemy, what hope remains for the atmosphere above it? As we descend toward the rusty surface of Mars, drawn by the dream of colonization, we must first pass through something that appears almost invisible, yet is among the most lethal aspects of the Red Planet, the Martian atmosphere, or rather, the ghostly whisper of what might once have been an atmosphere. Here, wrapped around this barren world is not a protective blanket like Earth's sky, but a hostile void that seeks to destroy any unprotected human body within seconds. This is not air. This is the threshold between existence and oblivion, stretched paper-thin across an entire planet. The atmospheric pressure on Mars measures just 0.6% of Earth's sea level pressure. To understand what this means, we must journey upward through Earth's atmosphere to the very edge of survivability. At approximately 63,000 feet, roughly 19 kilometers above Earth's surface, we reach what aerospace medicine calls the Armstrong limit. This is the altitude where atmospheric pressure drops so low that water boils at human body temperature. Mars exists permanently below this threshold. Standing on the Martian surface is equivalent to being suspended at 100,000 feet above Earth, higher than any aircraft routinely flies, in a realm where the atmosphere is so tenuous it barely exists at all. What happens to an unprotected human body in this near vacuum is not instantaneous death, but something far more terrifying. A progression of catastrophic failures, each more agonizing than the last. Within seconds, the moisture on your tongue, in your eyes, and within your lungs begins to boil. Not from heat, but from the absence of pressure. This is ebulism, the formation of water vapor bubbles in bodily fluids. Your soft tissues swell. Your lungs, if you make the fatal mistake of holding your breath, rupture from the pressure differential between your body's interior and the void outside. Oxygen vanishes from your bloodstream. Within 15 seconds you lose consciousness. Within 2 minutes, without immediate repressurization, death becomes inevitable. This is the reality that awaits beyond every habitat wall, every airlock, every sealed seam in every spacesuit. Mars does not offer the luxury of a slow death. It offers explosive decompression, a violence of physics that transforms the human body from a living organism into a biological failure within the span of a single breath. But pressure is merely the first betrayal of Mars's atmosphere. The temperature extremes create a second layer of hostility that compounds every engineering challenge. Mars is a world of savage thermal swings. At the equator, during Martian summer, daytime temperatures can reach a deceptively pleasant 70 degrees, warm enough that you might imagine stepping outside in shirt sleeves. Yet as night falls, the temperature plummets to 100 degrees or lower. Near the poles, winter temperatures descend to 140 degrees, cold enough to freeze carbon dioxide from the air itself, creating vast seasonal ice caps made not of water, but of dry ice. These are not gradual seasonal changes. These are daily catastrophes. Every Martian day, called a sol, materials expand and contract through temperature ranges of over 170 degrees. Metals fatigue, seals crack, composites delaminate, plastics become brittle. Every structural component, every mechanical joint, every electrical connection experiences thermal stress cycles that would destroy most Earth-based technology within weeks. The habitat that keeps you alive is simultaneously being torn apart by the relentless expansion and contraction of its own materials, molecule by molecule, soul by soul. Maintaining survivable temperatures inside a habitat requires constant energy expenditure. Unlike Earth, where atmosphere itself provides thermal mass and moderate temperature swings, Mars offers no buffer. The thin atmosphere cannot hold heat. Buildings cool rapidly once the sun sets, losing warmth to the vacuum of space through radiation. Heating systems must run continuously through the Martian night, which lasts roughly as long as an Earth night, 12.5 hours of darkness during which every joule of heat must be manufactured, distributed, and maintained against an environment actively trying to freeze everything solid. The composition of Mars's atmosphere adds yet another dimension of impossibility. 95% carbon dioxide, less than 0% oxygen, trace amounts of nitrogen, argon, and other gases in proportions utterly unsuitable for human respiration. This is not an atmosphere that can be filtered or processed through a simple gas mask. This is an atmosphere that must be completely replaced, atom by atom, with breathable air manufactured from raw materials. Generating oxygen on Mars is theoretically possible through several methods. The most discussed involves using the carbon dioxide atmosphere itself, splitting CO2 molecules into carbon monoxide and oxygen through electrolysis or chemical reduction. NASA's MOXIE experiment, delivered to Mars aboard the Perseverance rover, has demonstrated this technology on a small scale, producing a few grams of oxygen per hour. But scaling this process to support human life reveals staggering energy requirements. A single human requires approximately 800 grams of oxygen per day. A small colony of 10 people needs 8 kilograms daily. This oxygen must be generated continuously, without fail, every moment of every soul. The MOXIE unit requires substantial electrical power to produce even its modest output. Multiply this by the factors needed for human-scale life support, and the energy budget becomes astronomical. Solar panels constantly degraded by dust accumulation and insufficient sunlight struggle to provide adequate power. Nuclear reactors, though more reliable, add mass, complexity, and their own catastrophic failure modes to an already precarious system. And then there are the dust storms. Mars is a world of dust, fine particles of oxidized iron that permeate everything. Local dust storms occur frequently. Regional storms can cover areas the size of continents. But every few Martian years, approximately once per decade in Earth time, something far more ominous occurs. A global dust storm envelops the entire planet, blocking sunlight for weeks or months at a time. In 2018, such a storm ended the Opportunity rover's mission. Solar panels covered in dust and deprived of sunlight could no longer generate power. The rover's batteries depleted. Systems froze. Communication ceased. This was a robot designed to endure such conditions, with no biological needs, no requirements for heat or air beyond what its electronics demanded. Yet it died in the darkness. Now imagine a human habitat during a global dust storm. Solar power drops to near zero. Battery reserves begin depleting. Energy must be rationed. Heating cycles reduce. Oxygen generation slows. Every system enters emergency conservation mode. The storm may last 60 sols, 90 sols, longer. There is no weather forecast that can predict when the dust will settle, when the sun will return, when power generation can resume. The colony sits in semi-darkness, cold creeping through the walls, carbon dioxide scrubbers working at reduced capacity, oxygen levels slowly declining, while inhabitants wait, ration air, and calculate how long their reserves will last. This is the energy crisis scenario that colony planners rarely discuss in public presentations. The scenario where every backup system is needed simultaneously, where redundancy is exhausted, where the technological debt comes due all at once. Because on Mars, every primary system requires a backup. Every backup requires a tertiary system. Every safety margin must account not just for normal operations, but for months-long catastrophes that provide no warning and offer no respite. The exponential complexity becomes overwhelming. A habitat needs power generation, which needs backup power, which needs energy storage systems, which need thermal management, which needs cooling systems, which need power, which need redundancy. Life support needs oxygen generation, carbon dioxide scrubbing, humidity control, temperature regulation, pressure maintenance, all operating continuously. Water recycling requires filtration, purification, storage, distribution, each with its own backups. Food production, waste management, medical facilities, communication systems, each layer adding mass, complexity, and additional points of failure. We often hear Mars colonies compared to Antarctic research stations, as though surviving the coldest place on Earth prepares us for Mars. This comparison reveals a profound misunderstanding of scale. Antarctica, for all its hostility, has breathable air. Researchers step outside in insulated clothing, not spacesuits. If equipment fails, they breathe while they repair it. If power fails, they do not suffocate in darkness. Supply ships arrive annually carrying food, fuel, and replacement parts. In emergencies, aircraft can evacuate personnel to civilization within hours. Mars offers none of these reprieves. There is no supply ship coming next season. There is no rescue aircraft. There is no breathable air outside the habitat. There is no civilization 8 hours away. Antarctica is a harsh environment surrounded by a habitable planet. Mars is an uninhabitable world surrounded by infinite vacuum. The comparison insults the magnitude of the challenge. The single point of failure catastrophe haunts every Mars habitat design. One micrometeorite puncture in the wrong location, one manufacturing defect in a pressure seal, one software error in an airlock controller, one moment of human error during a maintenance procedure. Any of these in the unforgiving near vacuum of Mars means explosive decompression. Alarms sound. Emergency bulkheads slam shut. If they function correctly, pressure drops catastrophically. Humans in the affected section have seconds perhaps to don emergency respirators if they are nearby, if they function, if there is time. In the worst scenarios, cascading failures overwhelm even the most carefully designed emergency systems. A habitat breach in a central module depressurizes adjacent sections. Backup power systems stressed by the emergency begin failing. Life support computers, damaged by the initial event, provide conflicting information. Crew members, already hypoxic from oxygen loss, struggle to make decisions as their cognitive functions decline. Within minutes, what began as a single point of failure becomes a colony-wide extinction event. This is not speculation or dramatization. This is the engineering reality that every spacecraft designer, every habitat architect, every life support engineer confronts when calculating mass margins and redundancy requirements. The atmosphere of Mars, or rather its absence, creates an environment where the difference between survival and death is measured in millimeters of hull thickness, in the reliability of a single valve, in the split-second response of an emergency system that must function perfectly despite months of thermal cycling, dust infiltration, and radiation exposure. As we contemplate sending humans to live on Mars, we must confront the truth that the Martian atmosphere is not merely thin or inconvenient. It is fundamentally incompatible with human life in ways that cannot be engineered around, only endlessly defended against. Every breath on Mars must be manufactured. Every moment of warmth must be generated. Every second of existence must be maintained by technology that itself degrades in an environment designed to destroy it. The atmosphere that barely exists becomes the obstacle that permeates everything. It makes Mars not a frontier to be settled, but a hostile void to be temporarily survived, at extraordinary cost, with no margin for error and no possibility of true permanence. Here, wrapped in this gossamer shroud of carbon dioxide and cold, the dream of colonization confronts the physics of extinction. As our journey through Mars's hostile realities continues, we arrive at perhaps the most insidious threat of all, one that cannot be shielded against, filtered out, or engineered away. It is written into the very fabric of the planet itself, woven into the curvature of space-time around Mars's modest mass. This threat is gravity, or rather, the profound and irreversible absence of it. Mars pulls at objects with only 38% the force of Earth. At first consideration, this sounds almost manageable, perhaps even advantageous. Lighter loads to carry, less strain on structures, the romantic notion of bounding across the Martian landscape in great leaps, like astronauts dancing across the moon. But gravity is not merely about weight. It is the silent architect of every biological system in our bodies, the invisible sculptor that shaped life on Earth across billions of years of evolution. Remove it, diminish it, and the human body does not adapt. It begins to fail. The deterioration starts immediately, from the very first moment a colonist sets foot on Martian soil. Their skeleton, that magnificent internal framework that has supported their every movement since childhood, begins to dissolve. Studies of astronauts in microgravity reveal bone density loss at a rate of 1 to 2% per month. On Mars, with its fractional gravity, the loss is slower but relentless and cumulative. Month after month, calcium leaches from bones into the bloodstream, where it serves no purpose except to increase the risk of kidney stones. The skeleton becomes porous, brittle, a shadow of its former strength. This is not temporary muscle soreness or fatigue. This is osteoporosis on an accelerated timeline, transforming healthy adults into frail versions of themselves within years. Hip bones thin, vertebrae compress. The femur, once capable of supporting hundreds of pounds of force, becomes vulnerable to fractures from the simplest misstep. A colonist who has lived on Mars for 5 years may possess the skeletal structure of an elderly person on Earth, their bones hollowed out by the planet's weak embrace. The skeleton, however, is only the beginning. Muscles, those engines of movement that propel us through life, begin their own inexorable decline. In Earth's gravity, every moment of standing, walking, or lifting requires muscular effort that maintains strength and mass. On Mars, these same actions demand far less force. The body, efficient and adaptive, responds logically. It eliminates what it no longer needs. Muscle fibers atrophy, mass diminishes. What was once solid becomes soft, weak, insufficient. The legs suffer first and most severely. The calves, the thighs, the gluteal muscles that power every step, they waste away in Mars's gentle pull. Studies of astronauts returning from extended stays on the International Space Station show muscle mass reductions of up to 20% or more. On Mars, the process continues indefinitely, never ceasing, never reversing. A colonist who once ran marathons may eventually struggle to walk. Their body has become perfectly adapted to Mars and catastrophically unsuited to Earth. But perhaps the most concerning degradation occurs in the muscle we cannot see, the one that beats ceaselessly from our first moment to our last. The heart. On Earth, this remarkable organ pumps blood against gravity's constant downward pull, maintaining pressure, ensuring circulation to the brain and extremities. It is a workout that never ends, strengthening the heart with every beat. On Mars, that resistance diminishes. The heart no longer needs to work as hard. And so, like all muscles freed from their burden, it weakens. Cardiovascular deconditioning transforms astronauts' hearts into smaller, less efficient organs. The muscle walls thin, the chamber volume decreases, blood pressure drops, orthostatic intolerance develops, meaning that even minor position changes can cause dizziness or fainting. This is the human body optimizing itself for an alien world, becoming a Martian organism ill-suited for the planet that created it. The colonist's heart, once robust and powerful, becomes a diminished engine, barely adequate for the reduced demands of Mars, completely inadequate for Earth. Then there is the mystery of vision, a problem so unexpected and troubling that it has reshaped our understanding of long-duration spaceflight. Astronauts returning from extended missions aboard the International Space Station report disturbing visual changes. Some experience blurred vision. Others show physical deformations of the eyeball itself, flattening at the back, swelling of the optic nerve, changes in the retina. The cause appears to be intracranial pressure, the fluid pressure within the skull. On Earth, gravity constantly pulls bodily fluids downward, maintaining a pressure gradient from head to feet. In reduced gravity, this gradient diminishes. Fluids shift toward the head, increasing pressure within the skull. This pressure, sustained over months and years, physically deforms the eye from behind, pushing against delicate structures that evolved in Earth's gravitational environment. The vision changes are not always reversible. Some astronauts return with permanent alterations to their eyesight, a testament written in their bodies to the time they spent away from Earth's pull. On Mars, with its intermediate gravity, the effect may be less severe than in complete microgravity, but it does not disappear. Colonists living for years on the red planet would experience this chronic elevation of intracranial pressure continuously. The slow, insidious deformation of their eyes would proceed unchecked, potentially robbing them of clear vision by middle age, transforming a sensory system honed across millions of years into something compromised and failing. Even the immune system, that invisible guardian that protects us from disease and infection, weakens in reduced gravity. Studies have shown that spaceflight alters immune cell function at the cellular level. White blood cells become less effective. The body's ability to mount inflammatory responses diminishes. Wounds heal more slowly. Infections that would be minor on Earth become potentially serious. The mechanism is not entirely understood, but evidence suggests that gravity itself plays a role in cellular function, in gene expression, in the fundamental processes that keep us healthy. A Mars colonist, already exposed to elevated radiation, toxic soil, and a hostile environment, would face these threats with an immune system operating at reduced capacity. Every cut, every illness, every pathogen becomes more dangerous. The compounding effects are terrifying. A population already physiologically compromised by bone loss, muscle atrophy, and cardiovascular deconditioning now possesses weakened defenses against disease. The colony becomes not just a settlement on an alien world, but a population in perpetual medical crisis. Yet all of these effects, devastating as they are, pale before the ultimate consequence, the return problem. After years on Mars, after the body has adapted to its reduced gravity, what happens when a colonist attempts to return to Earth? The answer is both simple and horrifying. They cannot. Earth's gravity, the very force that nurtured and shaped human evolution, becomes a prison they cannot escape and a home they cannot return to. A colonist who has spent 5, 10, 15 years on Mars would possess bones too fragile to support their own weight on Earth. Their muscles, atrophied and weak, could not lift their body against the planet's pull. Their heart, diminished and deconditioned, could not maintain adequate circulation against Earth's gravitational gradient. They would collapse. They would break. Earth itself would crush them under the weight of normal gravity. This is not speculation. It is the mathematical certainty of physics and biology combined. Astronauts returning from 6-month stays on the International Space Station require months of rehabilitation just to walk normally again, and they return from microgravity, not Mars's intermediate state. A colonist returning from Mars after years would face challenges that may prove insurmountable. They have become, in the most literal sense, aliens to their own homeworld. Mars has claimed them not through death, but through transformation. They are alive, but they are no longer truly human in the earthbound sense. They are Martians, permanently and irreversibly. And what of children born on Mars? This question opens an abyss of ethical horror. A human fetus developing in reduced gravity, bones forming under weaker stress, muscles growing in diminished resistance, a heart adapting to easier circulation. These children would never possess bodies compatible with Earth. They would be born into a biological trap, citizens of Mars not by choice but by the circumstances of their development. Their skeletons would form differently, lighter and more fragile. Their muscles would develop for Martian conditions. Their cardiovascular systems would be calibrated for 38% gravity. Such children could never visit Earth. The gravity would be lethal. They would be prisoners of Mars from their first breath, their entire existence confined to a single hostile planet, unable to experience the world their parents came from, unable to feel rain on their skin, or breathe unfiltered air or see a blue sky. They would inherit a diminished existence, and they would have no choice in the matter. This is not colonization. It is the creation of a stranded population, genetically human but physiologically alien, cut off from humanity's homeworld by the simple, immutable mathematics of gravitational acceleration. The most troubling aspect of Mars's gravitational trap is that we have no solution. Exercise regimens, so effective at maintaining fitness on Earth, prove woefully inadequate in reduced gravity. Astronauts on the International Space Station exercise for hours each day, using resistance machines and treadmills specifically designed for spaceflight. Yet despite these efforts, bone loss continues, muscle atrophy persists, the cardiovascular deconditioning advances. Exercise can slow the decline, but cannot stop it. The body requires the constant, inescapable pull of Earth's gravity to maintain itself. Nothing less will suffice. Artificial gravity generated by rotation remains theoretical for planetary colonies. We might build spinning habitats in space, but we cannot spin Mars. The planet's gravity is fixed, immutable, insufficient. There are no centrifuges large enough, no medical interventions effective enough, no technological solutions on any conceivable horizon that can preserve human physiology in Mars's weak gravitational field indefinitely. This is the gravity well of despair. Not a trap of attraction that pulls spacecraft inward, but a biological trap that transforms human bodies into forms that cannot escape. Mars's weak gravity seems gentle, even welcoming, until we understand its true nature. It is not a softer version of Earth's pull. It is a fundamentally different environment, one that unravels the human form with patient, relentless efficiency. Every day on Mars is another day of deterioration, another step away from the body that evolved under Earth's familiar weight, another movement toward a physiology that cannot return home. The gravity well of despair is invisible, unfelt, and absolute. It asks no permission. It shows no mercy. It simply is, a fundamental property of a planet that, despite our dreams and ambitions, was never meant to cradle human life. We have journeyed across the Martian surface, survived the radiation, endured the poisonous soil, and felt the slow collapse of our bodies in the weak gravity. Yet even if we could somehow overcome these physical torments, we face perhaps the most insurmountable obstacle of all. Mars has nothing we need. The red planet presents us with what appears to be a cosmic deception, a mirage of resources that dissolves upon close examination. What looks like water is locked away and contaminated. What appears to be mineral wealth is scattered and inaccessible. What seems like opportunity is, in truth, an economic void so vast it makes the emptiness of space seem crowded by comparison. Let us begin with the most fundamental resource, the substance without which no colony can exist: water. We are told that Mars has ice, vast quantities of it, trapped beneath the surface and frozen at the poles. This is true. But the reality of Martian water is far more troubling than the dream suggests. This ice is not conveniently located near the surface in temperate regions where humans might survive. It lies buried beneath meters of regolith and dust, or concentrated in the polar regions where temperatures plunge to negative 125 degrees Celsius. Extracting this ice is not a matter of simply digging a well or melting surface frost. It requires massive industrial equipment, enormous energy expenditure, and continuous operation in an environment that destroys machinery with its dust and temperature extremes. Even if we could extract this water, we face a deeper problem, one that reveals how thoroughly Mars betrays those who seek to use its resources. The water ice on Mars is not pure. It is contaminated with perchlorates, the same toxic compounds that saturate the soil. These chemicals do not simply rinse away. They dissolve into the water, creating a solution that is poisonous to humans and corrosive to equipment. Purifying this water requires complex filtration systems, reverse osmosis membranes, and chemical treatment processes. Each of these technologies demands energy, replacement parts, and technical expertise. Each represents another link in a chain of dependency that stretches back to Earth across 225 million kilometers of void. The energy required to extract, melt, purify, and distribute water on Mars is staggering. And this brings us to the second great resource Mirage, energy itself. Mars receives only 43% of the sunlight that reaches Earth. Solar panels, already inefficient in Earth's bright daylight, become even less effective on Mars. Dust storms that can last weeks or months coat panels in fine particles, reducing their output to nearly nothing. The weak sun, filtered through the thin, dusty atmosphere, provides barely enough energy to sustain basic life support, let alone power the industrial operations necessary for a self-sustaining colony. Could we use nuclear power instead? In theory, yes. But nuclear reactors require fuel, uranium or plutonium, materials that must be mined, refined, and processed through extraordinarily complex industrial chains. Mars has no concentrated uranium deposits that we know of. Even if such deposits existed, Mars lacks the billions of years of geological processes that concentrate ores on Earth. Our planet's active tectonics, its liquid water cycles, its volcanic activity, all of these have worked across deep time to gather scattered elements into rich veins and deposits. Mars, geologically dead for billions of years, offers only diffuse minerals scattered across its surface, requiring vast amounts of material to be processed for minimal return. This is the raw materials problem, and it extends far beyond uranium. Every element on Mars exists in its most inconvenient form. Iron is present, but not as the concentrated ore bodies formed by Earth's hydrothermal processes. Aluminum exists, but extracting it from Martian regolith requires the same energy-intensive processes we use on Earth, except without Earth's infrastructure, without its abundant energy, without its logistics networks. To extract 1 kilogram of pure metal on Mars might require processing tons of regolith, consuming megawatts of power and operating machinery that has no replacement parts within 225 million kilometers. The manufacturing impossibility becomes clear when we consider what a modern colony actually needs. Let us imagine a single computer chip, the kind found in every electronic device, every medical instrument, every communication system. Creating this chip requires not dozens, but thousands of prior manufacturing steps. It requires ultra-pure silicon, grown as perfect crystals. It requires clean rooms with air filtration systems measuring particles in nanometers. It requires photolithography equipment using ultraviolet light to etch circuits smaller than bacteria. It requires rare earth elements, chemical etching processes, plasma deposition systems, and testing equipment of staggering complexity. Every single one of these steps depends on equipment and materials that themselves require thousands of manufacturing steps. The machines that make computer chips require bearings made from precisely formulated steel. These bearings require furnaces that maintain exact temperatures. These furnaces require ceramic insulation made from materials processed in other facilities. The supply chain does not branch, it explodes, creating a web of interdependence so vast that even Earth, with 8 billion people and 10,000 years of accumulated technology, struggles to maintain it. Some chips can only be manufactured in 3 facilities worldwide. To replicate even one of these facilities on Mars is not difficult, it is impossible. The same applies to pharmaceuticals, to advanced materials, to synthetic polymers, to ball bearings, to electrical wire, to glass, to rubber seals, to lubricants, to every single item that makes technological civilization possible. A Mars colony cannot manufacture these things. It can only import them from Earth, and in doing so it becomes not a colony, but a hostage, a perpetually dependent outpost sustained only by a supply line stretching across interplanetary space. This brings us to the economic reality, the calculation that destroys any practical argument for Mars colonization. A resource is only valuable if it can be sold. A colony is only sustainable if it can produce something worth more than the cost of its supply line. Mars has nothing to export. It has no gold concentrated enough to justify transportation costs. It has no rare elements unavailable on Earth or in the asteroid belt, which is both closer and richer in resources. It has no manufactured goods that could not be made more easily in Earth orbit. It has no agricultural products, no intellectual property, no services that justify the expense of maintaining human presence on its surface. The cost to transport 1 kilogram of cargo to Mars exceeds tens of thousands of dollars, possibly hundreds of thousands depending on the mission architecture. To make a profit, Mars would need to export something worth more per kilogram than platinum, than diamonds, than the most expensive materials known to humanity. No such substance exists on Mars. The red planet offers only regolith and rust, materials so common they are worthless. To sustain a colony through exports is to sustain it through fantasy. Even if we abandon economics and imagine Mars as a purely scientific or idealistic venture, supported indefinitely by Earth, we face the tyranny of orbital mechanics. The planets align favorably for travel only once every 26 months, during what is called the synodic period. This means that resupply missions can only launch during narrow windows separated by more than 2 years. If a critical component fails, if a medical emergency occurs, if a crop fails or a water purification system breaks, help is not hours or days away. It is months away at best, and if the launch window has passed, it may be more than 2 years away. Imagine living with that knowledge. Imagine knowing that if something goes wrong, truly wrong, there is no rescue. No helicopter can fly to you. No ship can sail to your location. No ambulance can rush you to a hospital. The nearest help is on another planet separated by a gulf of space so vast that light itself takes 20 minutes to cross it at closest approach. This is not exploration in the way humans have ever understood it. It is exile with resupply. We need only look at the International Space Station to understand the impossibility of self-sufficiency. The ISS orbits 400 kilometers above Earth's surface, closer to help than most cities are to their neighboring capitals. It is crewed by the most highly trained humans alive, supported by the combined resources of multiple space agencies with budgets in the billions. And after more than 20 years of continuous habitation, the ISS is not even remotely self-sufficient. It requires constant resupply of food, water, spare parts and equipment. It recycles some resources, but nowhere near enough to sustain itself indefinitely. Every few months, cargo vessels dock with tons of supplies. Without them, the station would be abandoned within months. If we cannot achieve self-sufficiency in Earth orbit, where resupply is easy and rescue is possible within hours, how can we imagine achieving it on Mars, where resupply takes years and rescue is impossible? The ISS proves that even with Earth's entire industrial base a few hundred kilometers away, humans cannot yet create closed-loop systems that sustain themselves indefinitely. To expect this on Mars with its toxic soil, its killing radiation, its atmosphere that wants us dead, is not optimism. It is delusion. The resource mirage on Mars is complete. Every necessity exists in its most inconvenient form. Every extraction requires energy we cannot generate. Every manufacturing process requires equipment we cannot build. Every spare part must come from Earth. Every complex item demands a supply chain we cannot replicate. The red planet offers us nothing but the opportunity to spend vast fortunes maintaining a fragile outpost that will never produce anything of value, that will never sustain itself, that will exist only as a monument to the limits of human ambition. As we stand on the Martian surface surrounded by rust-red emptiness, we must ask ourselves, what were we hoping to find here? What resources did we imagine would sustain us? The answer is uncomfortable. We were sustained not by Martian resources but by earthly dreams. We came here carried by hope, by vision, by the same impulse that drove explorers across Earth's oceans and deserts. But those explorers found new lands with breathable air, drinkable water, and soil that could grow food. Mars offers none of these things. It offers only the illusion of them, a mirage that recedes with every step we take towards self-sufficiency. In the cold mathematics of resources and manufacturing, of supply chains and energy budgets, Mars reveals itself not as humanity's second home, but as its most expensive graveyard. Beyond the radiation burns, beyond the toxic soil, beyond the crushing gravity and suffocating atmosphere, Mars presents a final barrier to colonization, one that cannot be shielded against with any material or technology. It is the invisible weight of isolation itself. The quiet erosion of the human mind trapped millions of miles from home with no possibility of return. This is not science fiction. This is the documented reality of what happens to human consciousness when confined, isolated, and severed from the sensory world that shaped our evolution. Mars may kill the body slowly, but it destroys the mind with relentless efficiency. We have already glimpsed this abyss here on Earth, in the frozen research stations of Antarctica, in the sealed chambers of submarines cruising beneath polar ice, in isolation experiments conducted by space agencies around the world. The same patterns emerge with disturbing consistency. Humans break, not all at once, but gradually, predictably, inevitably. In these environments, researchers have documented what they call the winter over syndrome, a constellation of psychological symptoms that appear after prolonged isolation: sleep disturbances, cognitive impairment, emotional volatility, depression that settles in like a fog and refuses to lift. These are not weak individuals. They are trained professionals, screened for psychological resilience, supported by regular communication with the outside world, and still they fracture. Antarctica offers perhaps the closest analogy to a Martian colony. The cold is lethal, the environment is hostile, resupply is seasonal at best, and yet Antarctic stations have something Mars will never provide: the knowledge that rescue is possible, that evacuation, while difficult, is achievable, that in a true emergency someone can come. Mars offers no such comfort. On Mars there is no rescue, there is no evacuation. There is only the red dust and the thin air and the knowledge that you are farther from help than any human has ever been. This psychological distinction is not trivial. It is foundational. The human mind calibrates its resilience based partly on the existence of an escape route. Remove that option entirely, and the psychological landscape transforms into something far darker. Then there is the communication delay, a barrier more profound than most realize. Mars, at its closest approach to Earth, is still over 33 million miles away. At its farthest, that distance extends beyond 140 million miles. Light itself, the fastest thing in the universe, takes between 4 and 24 minutes to cross this void. This means every message sent from Mars to Earth requires a minimum of 8 minutes for a response at best, and up to 48 minutes during orbital opposition. There are no phone calls, no video chats, no real-time connection with loved ones, with mission control, with the civilization you left behind. Every conversation is asynchronous, disjointed, like shouting into a well and waiting endlessly for an echo that may or may not come. Psychologically, this delay severs one of humanity's most fundamental needs: immediate social connection. The back-and-forth rhythm of conversation, the subtle cues of tone and timing, the comfort of being heard and acknowledged in the moment, all of this vanishes. What remains are recorded messages, time-stamped artifacts of emotions that were felt minutes or hours ago. By the time you receive comfort, the moment that needed it has already passed. By the time you share joy, it arrives stale and distant. The colonists on Mars will watch Earth not as participants, but as historians, viewing a world that moves on without them, a world they can see but never touch. This communication barrier creates what psychologists call temporal isolation, a uniqueness of being unstuck from the social rhythm of your species. On Earth, even the most isolated individuals exist within the same flow of time. Events happen simultaneously. News is immediate. Connection, even if delayed by hours, is still measured in the same day. On Mars, time itself becomes fractured. While you sleep, Earth experiences a different present. While you work, Earth moves through its own separate reality. You're not simply far from home, you're temporarily adrift, living in a pocket of existence that lags behind the rest of humanity by the speed of light itself. Inside the Martian habitat, the psychological pressure intensifies. Confined environment psychosis is not theoretical. It is observed, documented, and well understood from decades of submarine operations and space station research. When humans are sealed in small spaces for extended periods, predictable psychological degradation occurs. Aggression increases. Tolerance for minor irritations evaporates. Cognitive function declines. Tasks that once seemed simple become sources of frustration. Memory degrades. Attention narrows. The mind, evolved for vast landscapes and varied stimuli, begins to atrophy in the sensory monotony of artificial habitats. The Martian colony will be small, perhaps a few dozen individuals at most, living in pressurized modules barely larger than a few houses combined. There is no privacy, no solitude, no escape from the presence of others. Every sound, every smell, every habit of every other person becomes unavoidable. Research from long-duration submarine missions reveals that interpersonal conflict becomes the primary threat to mission success, far exceeding technical failures. Crew members who began as friends become adversaries over trivial disagreements. Resentments fester. Alliances form and dissolve. In one documented Antarctic incident, a researcher attacked a colleague with an axe over a dispute about a chess game. The human psyche, compressed and isolated, becomes volatile and unpredictable. Historical space missions have already demonstrated these fractures. The Soviet Salyut 7 mission experienced severe interpersonal breakdowns. Skylab crews reported growing tensions and psychological exhaustion. The Mars 500 simulation project, which sealed 6 volunteers in a mock Mars habitat for 520 days, revealed significant psychological strain, social withdrawal and cognitive decline, despite being safely on Earth with the knowledge they could leave at any time. On Mars, without that safety valve, the psychological descent would be steeper and darker. Then there is sensory deprivation, a form of torture that Mars administers continuously. Earth is a symphony of sensory experience. The wind carries scents of grass, rain, ocean salt. Seasons change the quality of light. Birds call at dawn, trees rustle, thunder rumbles, clouds shift and reshape. This constant variation is not merely pleasant, it is neurologically essential. The human brain requires sensory novelty to maintain healthy function. On Mars, there is none. The sky is always rust-coloured, tinged with pink dust. The wind, when it blows, is thin and silent, too weak to rustle anything. There are no smells except the recycled air of the habitat, no sounds except the hum of life support systems and the muffled voices of other colonists. No weather variations, no seasons that matter, No natural cycles except the Martian day that stretches 37 minutes longer than Earth's, gradually desynchronizing your circadian rhythm from the patterns your biology has followed for millions of years. This sensory monotony creates a condition known as environmental understimulation. The brain, deprived of varied input, begins to generate its own. Hallucinations become common. Phantom sounds and images appear in the corners of perception. Time perception distorts. Days blur together into an undifferentiated sameness. Antarctic researchers report losing track of time entirely, unable to distinguish Tuesday from Saturday, morning from evening. The mind becomes unmoored from temporal structure. On Mars, this will not be a temporary condition. It will be permanent. And then, the most horrifying scenario of all, the suicide problem. In isolated, confined environments, suicidal ideation increases dramatically. On submarines, on research stations, in space simulations, the question eventually surfaces in the minds of participants: what if I simply wanted to leave? On Earth, even in Antarctica, this question has an answer. Difficult perhaps, but possible. On Mars, the answer is final and absolute. You cannot. There is no leaving, no emergency shuttle home, no rescue mission that could arrive in time. The psychological impact of this permanence cannot be overstated. Knowing that you are trapped irrevocably for the remainder of your life creates a form of existential despair that no psychological screening can fully predict or prevent. Worse still, suicide on Mars becomes a social weapon. In a small, interdependent colony, one person's death affects everyone. Life support systems are calibrated for specific numbers. Psychological morale is fragile. One suicide could trigger a cascade, a psychological contagion that spreads through the colony like a virus. Earth-based isolated communities have experienced this. In the 1970s, a wave of suicides swept through Arctic research stations. The phenomenon is called cluster suicide, and it emerges precisely in environments like Mars will create. Small, isolated, inescapable, and psychologically strained. The social dynamics of such a colony would inevitably decay into dysfunction. Research on small isolated groups consistently shows the emergence of rigid hierarchies, scapegoating, and social fragmentation. Someone will be blamed for problems, real or imagined. Factions will form. Power struggles will emerge over limited resources and social standing. Without the moderating influence of larger society, without escape, without new people to refresh social dynamics, the group calcifies into patterns that become increasingly toxic. Mars will not foster cooperation and unity. It will amplify humanity's worst social tendencies, concentrating them into a pressure cooker with no release valve. And if children are born on Mars, the horror deepens into generational trauma. A child raised in the confined habitats of Mars will never know Earth, never feel rain on their skin, never see an ocean, a forest, a mountain, never hear birds, never smell flowers, never feel the full weight of Earth's gravity, or breathe air that was not filtered through machines. Their entire sensory reality will be limited to artificial corridors, recycled air, and red dust visible through reinforced windows. Psychologically, what does this do to developing minds? We do not fully know, but research on children raised in extreme isolation suggests profound developmental consequences. Language delays, social impairments, inability to process complex emotional information. These children will be Martian not by choice but by birth, sentenced to a world that offers nothing their biology is designed to thrive within. The philosophical horror is inescapable. Imagine waking each day knowing you are 140 million miles from the world that created you, that everyone you knew on Earth is aging, dying, living lives you can only observe with a time delay measured in light minutes, that you will never again feel a breeze, hear rain, or see the colour green except in photographs, that every step outside your habitat requires a suit, every breath depends on machines, and every moment is lived in an environment actively hostile to your existence. This is not adventure. This is imprisonment. A prison with no parole, no possibility of escape, no hope of return. The mind, confronted with this reality day after day, year after year, begins to collapse inward, folding under the weight of permanent exile. Mars does not need to kill colonists with radiation or toxic soil. The isolation, the sensory deprivation, the communication void, and the inescapable permanence of exile will dismantle human psychology with methodical precision. We are not evolved for Mars, not physically, and certainly not mentally. The red planet offers no home, only a tomb for the mind, sealed beneath an alien sky, waiting endlessly for a rescue that will never come. And so we return, not to Mars, but to understanding, to the quiet realization that some dreams are more beautiful as dreams than they ever could be as reality. We've journeyed through 6 impossible barriers, each one a wall built not by human limitation, but by the fundamental laws of nature itself. The radiation that penetrates flesh and bone with invisible violence, the toxic soil that poisons everything it touches, the atmosphere so thin it offers neither breath nor protection, the gravity too weak to sustain human bodies across generations, the resources that exist only as mirages in marketing presentations, and finally the psychological abyss that awaits any who attempt to build a society in that barren void. Yet despite these truths, the dream persists. Why? Perhaps because humanity has always needed frontiers, always required horizons to chase. The colonization of Mars has become not a scientific endeavour, but a cultural mythology, a narrative woven from science fiction novels, billionaire egos, and our deepest desire to believe we can escape the consequences of our choices. It is easier to dream of terraforming another world than to repair the one beneath our feet. But dreams have costs. Every $1 trillion directed toward an impossible Martian colony is $1 trillion not spent healing Earth's wounds. It is hospitals not built, ecosystems not restored, technologies not developed to reverse the damage we have inflicted upon the only habitable world we know exists. The opportunity cost of the Martian fantasy is measured not in dollars alone, but in the futures we sacrifice on the altar of an impossible vision. There are better paths forward. The moon, just 3 days away, offers a genuine testing ground for off-world habitation without Mars's lethal radiation bombardment. Orbital habitats built in the microgravity of space itself could provide rotating sections that simulate Earth's gravity while accessing unlimited solar energy. Asteroid mining could provide resources without the need to climb in and out of planetary gravity wells. Even Venus, with its scorching surface, offers cloud layers where temperature and pressure match Earth's, where floating cities could drift through an atmosphere rich in resources. And Mars itself? Its true value lies not in colonization, but in exploration. Robotic missions can unlock its geological history, search for signs of ancient life, and teach us about planetary evolution without risking human lives. Science does not require sacrifice. Knowledge does not demand we send people to die slowly in the rust-coloured desert of an alien world. So here, at the end of our journey, we ask you to reflect with us. If this exploration has shifted your perspective, if these truths have given you pause, share your thoughts in the comments below. Tell us where in the world you're listening from as you drift towards sleep. Subscribe to continue these voyages through the cosmos and the truths it reveals. Like this video if it has changed how you see the future of humanity among the stars. The beautiful lie of Mars colonization has served its purpose. It has inspired us, driven technological advancement, and reminded us that we are a species that dreams beyond our atmosphere. But now we must wake from the dream and face a deeper truth. Earth is not a launching pad to be abandoned. It is not a rough draft to be discarded when we produce a second attempt. Earth is our only home. It is the single point of light in an infinite darkness where life has taken root and flourished. Our destiny is not to flee it, but to save it, to tend it, to recognize that the greatest frontier lies not in the cold distance of space, but in the warm complexity of the world that gave us birth. Thank you for watching, for thinking, for questioning. May you rest well, knowing that tomorrow we continue the work of preserving the only paradise we have ever known.